Hello everyone, welcome to listen our recent work about peer-survey recommendation system. I'm Huiqiang from Alibaba Group. It's the outlines of this talk. We first introduce the motivation of this work. Then I will give some basic information of our peer-survey recommendation system. I will talk about overview of design and give more details about different modules. We also provide some experiments and case study to quantify the performance of our approach. This work is motivated by widely exist substitutions in e-commerce. This figure shows product comments from Taobao.com, the largest e-commerce platform in China. We find that most of customers are willing to switch to substitutions if their favorite items are not available. This substitution is driven by out-of-stock factors. Actually, there are some other factors induce substitutions. Let's imagine if we have 4 items, laundry A, laundry B, laundry C, and laundry D. If we present laundry A, laundry B, and laundry C, the customer may prefer the laundry B. However, if we present laundry A, laundry C, and laundry D, customer may prefer laundry D. It's because these laundry have similar functions, and the customer may have right thinking preference. A recent survey also supports this phenomenon, so it's necessary to incorporate substitutions in recommendation system of e-commerce. Currently, recommendation system in e-commerce mainly focus improving accuracy of individual recommendation with new technologies, but they ignore the cross-item influence of item. And in this paper, we consider cross-item influence of items in e-commerce recommendation system, and we formally term this phenomenon as PARS effect. Of existing studies have considered this kind of information. They term it as contextual information. They include time, place, and peers within one institute into recommended system. Some of them also consider bundle recommendations and decode effects. However, none of them have explicitly considered Pearce effect. Indeed, incorporate Pearce effect into recommendation system is a challenging problem due to its combinatory nature. To address this challenge, in this paper we propose a generic model to capture customers' preference, and we also design some efficient algorithms to solve the corresponding recommendation problem. Before giving more details about our algorithm, let's have a rough overview of our recommender system and the traditional recommender system. The left-hand side shows the workflow of traditional recommender system. Traditional recommender system recall items from item corpus and make a personalized ranking before output the final result to end customer. This means traditional recommender system is driven by independently personalized recalling and ranking products. However, in our recommender systems, we recall items from item corpus, and we estimates customer substitution preference and find optimal recommendation results based on estimated customer preference. We also make personalized ranking before output the final results. This means Our peer-aware recommendation system is driven by peer-aware modeling and personalized recommendation. More specifically, we propose a conceptual framework for peer-effect modeling. We have two components. The first component is a preference estimator. The preference estimator acts as a customer preference generator, and it criticizes the recommendations based on customer preference estimated from historical data. The second component is a recommendation optimizer. The recommendation optimizer acting as a recommendation result generator. It optimizes recommendation results based on generated customer preference. These two components are iteratively trained and learned. We find the final results by training these two modules. Let's see the first component, preference estimation. To capture customer substitution preference, we propose a ranking-based customer choice model. Under this model, we assume customers are segmented by their substitution preference. Customer substitution preference is described by a ranking model. That is, their favorite item may have the highest rank. Just like this figure shows, assume we have 6 customer segmentations. Each customer segmentation have a corresponding permutation or ranking. For example, customer segmentation 1 may have item A as the first rank, but customer segmentation 2 may have item C as its first rank. So when we impose a distribution on these customer segmentations, we can quantify the impact of customer substitution on item sales. Now the task is how to learn this distribution from historical data. To learn this distribution, we propose mathematical programming. By solving this mathematical programming, we can get the optimal solution about distribution that consistent with our historical data. The second component is recommendation optimization. Given the estimated customer preference from the first component, this component is just needed to find the optimal recommendation results. This problem is similar with a kind of knapsack problem. Therefore, we come up with a mixed integer programming like this formulation shows. Solving this programming problem, we can get the optimal recommendation results. Due to limited time, I just present some basic idea, and behind the intuitions, more details can be found in our paper. To better solve these two problems, we also propose a decomposition algorithm. Under this algorithm, customer preference estimation and recommendation optimization problem are simultaneously proceeded. The optimal solution efficiently converge to the optimal. Now let's discuss experiments. We conduct offline evaluation and online evaluation to validate our approach. We have 4 benchmarks. The first one is matrix factorization. The second one is collaborative filtering. The third one is estimate then optimize. Actually, it's a variant of our approach. Our approach is estimate, why optimize. The last one is a wide and deep model. Let's see the first results. This result actually indicates the learnability of our approach. Here the x-axis is custom types. It actually indicates the complexity of custom substitution pattern. The y-axis is revenue. We can say both of estimate then optimize and estimate why optimize can achieve better performance than MF and CCF method. This means the proposed model have good learning ability on customer preference. The second result is about robustness of our approach. The x-axis is the perturbation of input data. The y-axis is the revenue. We find our approach have good performance even for the perturbation of input data is large. So our approach is robust to fluctuation of input data. Last, we provide case study under this online scenario. As this figure shows, the first line is the recommendation results and the baseline algorithm, and the second line is the recommendation results of our approaches. It's not hard to say. Our approach make recommendations within a more focused scenario. We focus on kitchen and household recommendations. We can find customer may have more purchase and our recommendation results if they have substitution preference. That's all about this talk. If you are interested in our topic or you have any questions, please contact me by this email. Thank you.